Hey everybody, I hope all is going well. So in this video, I'm going to show you guys how to implement some confidence intervals in the real world and show you how you can draw some conclusions from those. I'm going to use, we're going to make a confidence interval for per capita carbon dioxide emissions, which can have some important implications as we'll talk about a little bit more as we're going through that data. First, I was going to take this opportunity to help you guys out with a homework problem, as I will do from time to time. So I'm going to say bye to you real quick so you can see my screen. And I just wanted, a couple people asked me about this particular homework problem. It was homework chapter 7.5, and it was number 4D. So let's go ahead and take a look at that problem. And so down here, number 4. And so this says the Economic Policy Institute periodically issues reports on workers' wages. Suppose the Institute reported that mean wages for male college graduates were 37.39 per hour and for female college graduates were 27.83 per hour. Assume the standard deviation for male graduates 4.6, females is 4.1. So right there, they are telling us about the population mean and population standard deviations for male and female population graduate wages. Now I'm just going to jump to D because people were asking me some questions about that one. And this is going to be, what is the probability that a sample of 110 female graduates will provide a sample mean more than 0.6 or 60 cents below the population mean? So the population mean is 27.83. That's the information they told us up there. What's the probability that we're going to end up 60 cents below that is the question. So another way to ask that is, what's the probability that I take a sample of 110 female graduates and the sample mean of those wages is below $27.23, right? Because that would be 60 cents below. So thinking about what that looks like a little bit, we're going to be taking, we know that when we take a sample average, it comes from a normal distribution centered at the true population mean. So I drew this picture. We have the true mean mu centered at 27.83. 27.23 is our x value. We're looking for the probability of getting a sample in that region right there. Now, this is not 4.1, the standard deviation they gave us, because remember, the standard deviation of the sample means is the standard error. So I had to do some math to get there, which I'll show you now. So what I do for problems like these is I like to just make myself a little spreadsheet and write down what I'm going to need. So I was going to show you the standard way that you've been learning and a kind of quick Excel trick way we can do as well. So let's look back at our assignment real quick here. And so what we have is a population mean for the females of 27.83. So I'll just start filling out the spreadsheet I made for myself. So pop in. Standard deviation, in this case it's the population standard deviation. N is the sample size. So down here in the problem, they tell us they're going to take a sample of 110. So 110. Now I'm ready to calculate my standard error, right? That's equal to the standard deviation divided by the square root of the sample size. That's where I got that 0.39 in the picture that I showed you right here. So 0.39, that's why I put 0.39 there. Now our z statistic we're going to calculate, we're looking, remember our kind of x value, maybe I should put up there, is 27.23, because we're looking 60 cents below the population mean. Now, if I was going to write out the whole z-stat, I could probably write something like my particular value minus the population mean divided by the standard error. Or another way to do that, they say 0.6 below, so we could always do equals minus 0.6 divided by the standard error, and that's going to give us the same number. So just think about why that is. Here we were just taking the difference, but where did we get that difference? We took minus 0.6 from the population mean. Now, what's the probability of landing in that region? So traditionally, you would have gone and used one of your z-tables to get this probability, but Excel has a built-in z-table. That's just going to a normal dot distribution and finding a probability. X is kind of confusing because we're going to feed this a z-score or a z-value. That's the probability I'm looking to the left of. My mean, now that I've gone to a z-distribution, the mean of a z-distribution is 0. The standard deviation of a z-distribution is 1, and true. I'm pretty much always going to put true in these distribution calculators. So that tells me that the probability of landing to the left of 60 cents below the population mean wage is just about 6.24% or 0.0624. Now, this is kind of the traditional ways where we calculate z-statistics and then either go to our table or use Excel's built-in table, which is this formula, to find the probabilities. Now, Excel will do all this work for you in the background. We could do norm.dist, so that same formula. Click in our actual x value, 27.23. Tell it the population mean. Tell it the standard deviation, but the standard error, because we're thinking about the standard deviation of the sample mean here, comma, true. And it turns out that that gives me the same number. So that's kind of like the quick way of doing it. This is the doing all the steps way of doing it. And I wanted to show you that both of those are options for you. And so that is calculating these formulas by default, norm.dist, or there's another formula called equals t.dist, by the way, if we have a t-distribution. We're using a z-distribution here because we know the population standard deviation. Now, those by default always give the probability to the left of a number, which is what we wanted here, so it worked out. But note that we can always get the probability to the right. For example, if I wanted the probability of being greater than 0.6 below, I'd do 1 minus. There's a 93.75% chance or a 93.76% chance of landing above this number, which makes sense because there's a whole lot more area above. And we'd expect to land above that because remember, the population mean wage is up here in the middle at 27.83. So to take a big random sample like that and end up way over here in this tail, we have a pretty low probability of that event at just over 6%. So that's the first thing I wanted to show you guys. Some help with that homework problem. Now, the main point of this video is to show you guys how to implement some confidence intervals in the real world. I'm going to calculate some confidence interval for carbon emissions over time. And I was just poking around online and found this data from ourworldindata.org, which is an organization that provides a lot of free data. You might want to look into it later in class for your project. And then I just clicked on one of these, and I noticed down here that we could download this data. And what happened when I downloaded, it's always great to see that free download button when you're doing statistics. What happened is I was given this data set right here. So over in columns A through D. Now this is a huge data set. We can see that the count in just one column is 20,000. So I have more than 20,000 observations. So what I did is I thought it'd be interesting to create a confidence interval for per capita CO2 emissions for Canada, and then compare that to per capita CO2 emissions for the United States. And so we can build confidence intervals for each of those, and then we could compare the two confidence intervals and get some interesting information out of that. Now, what exactly are we measuring here? This is what, if I took the total amount of carbon dioxide emissions emitted from the country of Canada in 1950, and I divided by the population, I would get about 11 tons of CO2 per person. In the US in 1950, I would have gotten about 16 tons per person. And so the reason it makes sense to do per capita, which is dividing by person, it wouldn't make sense to compare CO2 emissions in China and Rhode Island, for example, because there's going to be a massive difference just based on population. So I want to implicitly control for that effect of a bigger population by dividing by it. So per capita is always a good thing to be working with if we're looking at country level or state level data, for example. Now, as you were learning in the last confidence intervals video, we need to collect some information to build our confidence intervals. And so just like in that homework example, I like to sort of build myself out a list of everything I'm going to need, and then I can just go start collecting it. So I'll zoom in a little bit here. By the way, I just went over here and I copied Canada and the United States out of this data set. So let's start calculating our individual statistics that we need to build confidence intervals. So our confidence intervals are always centered at our sample average. So I'll do equals average is the formula that gives us averages in Excel. Click on this top number, Shift Command or Shift Control down arrow will go to the bottom of your list of numbers. And now we see that the average in that column of data is 15.46 tons per person per year in Canada of emissions. Okay, next we're going to calculate the sample standard deviation. Why am I doing a sample standard deviation here? Because I don't know what the standard deviation is, so I have to estimate it. I have to use this data to estimate the standard deviation. The formula to do a sample standard deviation, notice if I just do STDEV, that's for standard deviation. There's a few different possibilities. You're pretty much always going to want S for sample standard deviation. Click on the top number, Shift Control down arrow or Shift Command down arrow, depending if you're on Windows or Mac. Now there is my standard deviation. Sample size is just how many observations are here. A nice formula in Excel that will give us that is just to simply count the number of cells, which apparently there are 69 observations in this data set. Now I'm ready to calculate the standard error, right? Because that's equal to the standard deviation divided by the sample size. So standard error here is 0.03756. Now we're going to build a 90% confidence interval. So when we're thinking about confidence intervals, we want to ask, how far away from my estimate of the mean do I have to go above and below in order to be 95% confident that the true population per capita CO2 emissions are within my confidence interval? Well, if we were thinking about our bell curve shape here, so just thinking of this type of picture, I probably have to give it a mean. Let's just make it 0, 1. And so we're thinking about our bell curve. We want to go above and below enough so that the shaded area in the middle is 95% or 0.95. So if I was thinking of starting at 0 or starting at X bar in the middle, I'd want to keep going up until there was only 2.5% in this tail. Because if there's 2.5% in this tail and 2.5% in this tail, that means there's 95% in the middle. Well, if I found the number over here such that 2.5% is in this tail, how much does that mean is to the left of that number? 97.5%. That is why I label these numbers T 0.975, 97.5% to the left of the T value that I'm going to feed you. So we have to use a T distribution here because we estimated the standard deviation using the sample standard deviation. So to do this, we use equals T dot INV. So we talked in a little bit ago about there's a t-distribution. This is the inverse of a t-distribution. So this one, I tell it a probability, it tells me a number. If I did t-distribution, I tell it a number, it tells me a probability. So I want it to tell me the number such that there's 97.5% to the left. Degrees of freedom is always your sample size minus 1. And so there we go. That says that we have to go 1.995 t's above the mean in order to have just 2.5% in that upper tail and 97.5 in the lower. Now, this is my standard error. This number can be thought of as how many standard errors I need to go above and below to maintain 95% in the middle. So I have to do equals, my margin of error is my standard error times how many standard errors I need to go. Okay? So we have X bar, that was the average. Our standard deviation. Sample size is just counting those values. Standard error, oops, I forgot to divide by the square root of my sample size. Maybe some of you guys got that before. So always a good thing to go check, because that gave us quite a different number right there, or 0.622. So the standard error is the standard deviation divided by the square root of the sample size, of course. Now, I'm ready to take my margin of error. That is the number that is subtracted and added from X bar. So for my lower bound of my confidence interval equals X bar minus this number. Upper bound equals X bar plus this number. Oops, no, not that number. This number. So what does this mean? This means that we are 95% confident that the true population mean CO2 emissions per person per year in Canada is between 14.8 and 16.08 tons approximately. Okay, so now we can do that over with our US data equals average equals standard deviation, sample standard deviation. Sample size, probably going to be the same thing, but it's always good to check by using the formula to tell you. Standard error. Let's try to remember the square root this time. There it is. Equals, this is going to be the same exact number we got before, right? Because we're going to do 97.5% to the left, and we have the same sample size. So that means we have the same degrees of freedom, 1.995. Yep, we got exactly the same number. So now my margin of error is my particular standard error times how many I need to go. Now let's look at that, a margin of error for the second. The margin of error is smaller in the US than it is in Canada. That means that CO2 emissions are more volatile over time in Canada than they are in the United States. Because of course CO2 emissions are going to vary for random reasons from year to year, right? Like, I don't know, for an extreme example, there might be a pandemic that causes everybody to stay home. And then CO2 emissions will probably decrease as a result. That would be a crazy example, though. That would probably never happen. So now I'm adding and subtracting my margin of error from my sample mean to get my confidence interval, right? Now, one thing we can say is now we can make a comparison. Notice that the upper limit of the 95% confidence interval is below the lower limit of the 95% confidence interval for the United States. That means that now we are quite confident that CO2 emissions per capita are higher in the United States and Canada. Notice that if I just compared the means, They definitely appear to be higher in the United States on average. But remember, sample means are random variables. And those random changes we observe over time could cause these numbers to be different. But now that I've built a confidence interval, I am much more confident that Canada truly does have lower emissions per capita than the United States. Now, a couple tricks I want to show you. This is kind of the longhand way of doing these confidence intervals in Excel, but Excel has a lot of powerful tools. So I wanted to show you another couple of ways you can calculate the margin of error. And then all you have to do is the adding and the subtracting from the mean. One way to do that is to use a function called confidence.t. Now we're doing t because this is a problem with a sample standard deviation. So that means we have to use a t distribution. They also have confidence interval.norm if you happen to be doing one with a normal distribution, like if you know the population sample standard deviation, or if you're doing a proportion problem. Here, however, we're doing t, open parentheses, alpha, we're going to do a 95% confidence interval. Alpha is the number on the outside. So if 95% is in the middle, that means 5% or 0.05 is on the outside. Standard deviation is going to be that guy right there that we calculated. Or notice we could even calculate the standard deviation right inside of this formula. So we could wrap one Excel formula in another. So now I'm just simply calculating the standard deviation there. Sample size, I could do the same thing here, do a count inside of that formula. So this would be a really compact way to do this in Excel, because now I'm just calculating everything all at one time. Close those parentheses. Notice that these two numbers are the same. Now we're going to be using something called the data analysis tool pack a lot later in the semester. It will also calculate a 95% confidence interval for you, or really any size. So my input range is going to be my CO2 emissions, because that's the data of interest. I included the label when I copied that, so it's important that I click this box that says labels in first row. It is grouped by columns, because I have a column of data. My variable is all in a column. You can highlight more than one column, and then it would calculate many different margin of errors for you at the same time. Now I will stick this, let's just put it right below these ones so we can compare. So I'm just telling it where I want my results. Now I'm going to do a confidence interval here. So confidence level for mean, 95%. I could change that if I wanted, but I do want a 95% confidence interval. So let's hit OK. There it is. And we see that all three times I got the same number. So I just wanted to show you there are many different ways to calculate a confidence interval in Excel. This is how, these are three of those ways. There are other ways you could probably do it. I will not repeat those ones for the United States too, because as you see, we'd get exactly the same numbers. But I'll go ahead and send you this spreadsheet with the video so you can check it out. This might be useful for future homeworks as well as exams. So please reach out to me if you have any questions. Okay, bye-bye.